This is a video on ANOVA. This is the last video of the entire class. So I hope that you've learned a lot from these videos and that you've enjoyed them and that they will help you as you take your final exam. And in the future, if you want to go back and learn more about statistics, try and remember what we did before, you're always welcome to come back and take a look at any of these videos. What we will be talking about today is first the F distribution. We've already had the uniform distribution, the normal distribution, the student's t distribution, and the chi-squared distribution. So this is the final distribution of the quarter called the F distribution, which will be used for the one-way ANOVA test. So we'll talk about the one-way ANOVA test, which is a test to find out if many quantitative variables have the same mean, or if they don't have the same mean. And then after that, we'll actually be officially done with the class, but we have had lots and lots of hypothesis tests. I think that it's a good idea to go back and say, well, how do we know what test to use? So I want to summarize all the different tests that we've had in this class. So let's move on and talk about the F distribution. So if you remember, the t distribution and the chi-squared distribution had a different distribution for each degrees of freedom. The F distribution is similar, but there are two types of degrees of freedom for the F distribution. There's the numerator degrees of freedom and the denominator degrees of freedom. So for each pair of degrees of freedom, we get a different curve. And these are the curves that are shown for 4 different pairs of degrees of freedom. You'll notice a few things. One is that there are no negative values under these curves. So that's the good news. We don't have to worry about left tail and right tail and two-tail test. There's just one type of test. It turns out to be a right tail test because there's just a right tail for these particular curves, for the F curve. So the horizontal axis will be the F axis. We've seen the x-axis, the z-axis, the t-axis, the chi-squared axis. This will be the F axis. The vertical axis is just a number, a mathy thing. Once we've decided what the value is for that F, we could talk about the area to the right of that value, and that will be the p-value. We've understood all these things before, so hopefully you still understand this today. The same idea. Now let's use the F distribution by talking about one-way ANOVA. So analysis of variance is what ANOVA stands for. And it's used when we want to test the claim that 3 or more populations have the same mean. The null hypothesis, H naught, will be that all the means are the same. Mu1 equals mu2 equals mu3, all the way to the last one equals mu, whatever this last one is, mu n. The alternative hypothesis, you'd think that maybe the opposite of all the means are the same is that all the means are different, but those aren't opposites. Because you could have maybe first 5 of them the same, and then the 6th one might be different, and the 7th and 8th one might be the same. So some could be the same, some could be different, and that still violates H naught. So the way of talking about the opposite of H naught is just in words, saying at least 2 of the means differ from each other. So it turns out that ANOVA is very difficult to use. There are many, many assumptions that we have to make in order to use ANOVA, or requirements that we have to check. So let me go over the requirements. This is just an elementary statistics course, So I don't expect you to fully understand how to check the requirements, but I do want you to be aware of the requirements. The first is that all population distributions are approximately normal. That's actually a very difficult requirement to have. Now, we can have the sampling distributions are approximately normal, but then remember we have to have greater than 30 for every single sample that we're looking at. So if we're comparing 10 different means, then we're going to have hundreds and hundreds that we have to sample. It's very difficult to use ANOVA. The next requirement is that all populations have the same standard deviation, or at least not too different if the sample sizes are nearly equal. I will not get into the details on how to check either of these two requirements, but I want you to be aware that don't just use ANOVA for really important research unless you've taken another statistics class and you understand how to check that these two assumptions are true. The next is what we've always been doing, is that the data collection uses simple random sampling, or at least you are approximating simple random sampling. In our first chapter, we talked about what it takes to be approximately simple random. You could do a stratified sampling technique or a cluster sampling technique, but don't use convenience sampling. The next is the samples are independent of each other. So we saw with two quantitative variables, we had independent samples, and then we had the paired dependent samples. So ANOVA does not work for dependent samples. That would be asking one person 10 questions and the next person the same 10 questions, etc., etc. Those would be dependent samples. This is for independent sampling. And then finally, the categorization of the sample is done in the same way for every other sample. So if we're using stratified sampling for one of them, we better use it for the others too. So make sure that we categorize, we just use the same processes for each of the samples that we take. So let's do an example. So the question is, are the mean driving speeds the same for Highway 50, Highway 89, and Pioneer Trail? So you could think that the police department might have clocked a bunch of the cars, and in the Highway 50 we had 58, 52, 51, etc., and then a bunch of speeds for 89 and a bunch of speeds for Pioneer Trail. And they want to find out if all the roads have the same average speed. So let's write down the null hypothesis. Notice we have three quantitative variables. The survey question is, how fast did that car go? And the answer is quantitative, 58 miles per hour. So H naught is that mu1, the mean speed on Highway 50, equals mu2, the mean speed on Highway 89, equals mu3, the mean speed on Pioneer Trail. And H1 is that at least two of these mean speeds differ from each other. Fortunately, the calculator can handle this. In the calculator, we're going to go to stat, tests, and then ANOVA. Then we'll use ANOVA L1, L2, L3. So let's go to our calculator. So here's the calculator. I hit the stat button. I need to enter my data. So I hit enter on edit. I need to clear my L1, L2, and L3. So let's do that. I go up to L3, hit clear, and enter, and do the same for L1 and L2. And then I just type in my numbers. For L1, that will be the first highway. So we got 58. Enter. And then all the way to 56. Enter. And then I go to L2, 43. Enter. and the final number is 58. And then I go to L3, 51, enter, 55, enter, and then finally 50, enter. So now that I have all of my data entered in the columns, I hit Stat again. I go to Tests. And not only is ANOVA the last test for this class, it's actually the last test for the calculator. So I will use the up arrow button to get to that last test. And you'll see ANOVA, and I hit Enter. Then I type second 1 for L1, comma, second 2 for L2, comma, second 3 for L3, end the parentheses, and hit Enter. So there we have it. Our F statistic, that's the test statistic, is about 1.92 or so. And the p-value is about 0.17. So let's go back to the PowerPoint. Now that we have the p-value, 0.175, notice that level of significance wasn't given in this problem. In the real world, no one gives you a level of significance. You look at the p-value and you make a decision. We have 0.175. That's bigger than any level of significance that we would ever use. So when we have a high p-value, the conclusion is fail to reject H0, the same as any other tests that we've done. That means there is insufficient evidence, and then we just state H0. Okay, or H1 since it's insufficient. And we say there is insufficient evidence to conclude that the population mean speeds on the 3 roads are not the same. So let's take a look at another example. So a study was done to see if the mean GPAs for in-state, out-of-state, and foreign students are different. What can be concluded at the 0.01 level of significance? So let's start out by talking about H0. First, this will be ANOVA because we have 3 different quantitative survey questions, and we want to find out if the means are not all the same. So H0 will be that mu1, the mean GPA for in-state students, equals mu2, the mean GPA for out-of-state students, equals mu3, the mean GPA for foreign students. And then H1 is that at least 2 of these mean GPAs differ from each other. Instead of going to the calculator on this, I want to show you what it looks like if you use a computer. Nobody really uses a calculator when it comes to truly doing statistics. Everybody uses computers. So this is what a readout would look like if you were using a computer. Lots and lots of things are given. We're given the 3 different variables. They are sample sizes, means, standard errors. We're also given all kinds of other math, and I'm not going to get into the details of this math, GFSS, MS. F statistic, that's our test statistic, is 13.47. And then the most important number of this entire course is always the p-value. And here the computer says less than 0.0001. So that's a tiny p-value. And when we have a tiny p-value, we can state our conclusion and say that there is statistically significant evidence to conclude that at least 2 of the population mean GPAs differ. So I'm going to show you one more example. This is the last example for the entire course of elementary statistics. And the question is, are the mean lifespans for dogs the same for different living conditions? And we have some data for dogs that live in a fenced yard, for dogs that really only live indoors, except maybe to take a walk on a leash, and then for dogs that are